Assalamualaikum and good day everyone. I hope you are doing well and ready to proceed with our lecture today. I am Puan Rafiza and I will be giving you a lecture for the course Discrete Mathematics. Before we start our lecture, how do you feel today? I hope you are in a good mood and stay focused and motivated to start the class. Today, we are going to continue learning proof techniques. I am going to explain the mathematical induction and recursive induction. Please give me your full attention so that you can follow my lecture and be able to answer your tutorial 5. During my previous lecture, I explained one of the proof techniques, that is rules of inference. Modus ponens, modus tollens, and hypothetical syllogism are some of the examples of rules of inference. Today, I am going to explain mathematical induction. Although I presented on this subtopic last week, I have been asked by some of the students to repeat explaining as some of you still don't get it. Suppose that we were presented with the following formula and were not shown how it was derived. So, how could we prove that for all integers, n is greater than or equals to 1? We could try many different values of n, but how can we know it works for all n that is greater than or equals to 1? The problem can be solved using mathematical induction, and it is used to prove that each statement in a list is true. Usually, the list is countably infinite. When solving the problem, there are 4 parts or steps to be taken: base step, inductive hypothesis, inductive step, and summary statement. Now, let us see the first example. Based on the question given on the slide, we should use mathematical induction to solve the problem. Now, let Pn be the predicate of the statement. We have to prove that P1 is true during the base step. When n equals to 1, we must show that the equation at our right-hand side is also 1. You have to replace n with 1 in the equation as shown on the slide. Since 2 over 2 gives us 1, thus it is proven that P1 is true. During the second step, you have to replace n with k as shown on the slide, and this step is called the inductive hypothesis. During the third step, that is the inductive step, we have to show that if pk is true, pk plus 1 is also true. So, we assume that pk with k greater than or equals to 1 is true during this third step. Thus, we must show that pk plus 1 is also true. From the equation, we have to replace n with k plus 1 as shown on the slide. From the equation highlighted, we know that k comes before k plus 1. Furthermore, we have to show that the left-hand side is equal to the right-hand side. This part can be replaced with the pk. Can you understand my explanation so far? Well, good. For those who are still confused, don't worry. You may ask me during your tutorial class or ask me through WhatsApp. Now, let us continue solving the equation. To solve the equation on our left-hand side, we have to change our k plus 1 so that our denominator is 2. So I have to multiply 2 to the numerator and denominator as shown on the slide. I hope you know what numerator and denominator are. The numerator is the upper part and the denominator is the lower part of our fraction. Since my denominator is the same, thus I can eliminate 2 from my calculation. Now I have to expand the bracket for the equation on both sides. We cannot leave the answer like this as we can still add up our k and 2k for both sides. Thus our final shows that both sides are equal. Since the value of our left-hand side and right-hand side are equal, the final step, a summary statement, can be concluded that P1 is true and Pk plus 1 is also true. By mathematical induction, Pn is true for all n that is greater than or equal to 1. If you find it difficult to understand, let us try another example for better understanding. In this example, we are supposed to prove that n is less than 2 to the power of n for all positive integers using mathematical induction. We are going to follow the 4 steps highlighted in our previous slides. We have to show that P1 is true for the first step. When n equals to 1, 2 to the power of 1 is equal to 2. Thus, it is true that 1 is less than 2. Next, we have to replace n with k as shown on the slide. This step is known as the inductive hypothesis. Since pk is true, we must show that pk plus 1 is also true for all k. To show that pk plus 1 is true, we replace n with k plus 1 as shown on the slide. From the first expression, we multiply 2 on both sides. Please note that 2k is the same as k plus k and not k multiplied by k. If k multiplied by k, it will give us k to the power of 2, and this is not tally with the 2k. Now, let us label this equation as the second expression. So far, we have 2 expressions. For k greater than 1, add both sides with k. Now, we label them as the third expression. From the second and the third expressions, we get k plus k less than 2 to the power of k plus 1 and k plus k greater than k plus 1. From these 2 expressions, we can arrange them as shown on the slide. If k plus 1 is less than k plus k and k plus k is less than 2 to the power of k plus 1, we can conclude that k plus 1 is less than 2 to the power of k plus 1. Thus, in our last step, a summary statement, we can say that P1 is true and pk plus 1 is true. By mathematical induction, n is less than 2 to the power of n for all n greater than or equal to 1. I hope you can understand how to prove the formula using mathematical induction from the previous 2 examples. Now, let us look at the recursive induction. We can use recursion to define functions, sequences, and sets. Sequences and functions can be proved using mathematical induction, or sets can be verified using structural induction. A recursive sequence, Fn, is also known as a recurrence sequence. It's a sequence of numbers indexed by an integer and is generated to solve a recurrence equation. The term recursive sequences can be denoted by several different notations as shown on the slide, where f is a symbol that represents the sequence. Sometimes it isn't easy to define a function or object explicitly. Hence, it is easier to define the function or object in terms of the function or object itself. This process is called recursion. For the Fibonacci numbers, Fn is defined by f0 equals 0, f1 equals 1. And for all n such that n is the member of the natural number where n is greater than or equal to 2, Fn is equals to Fn minus 1 plus Fn minus 2. Thus, f2 equals to 1, f3 equals to 2, f4 equals to 3, f5 equals to 5, f6 equals to 8, f7 equals to 13, f8 equals to 21, and etc. Do you know how to get the value for f2, f3, and f4? The following steps show how we get 1 for f2, 2 for f3, and 3 for f4. Since I have given you the example of getting values for f2, f3, and f4, I want you to take out a piece of paper and show me the steps to get the value for f5 to f8. Please WhatsApp me your answer. You may snap the picture. Don't forget to introduce your name and section when sending me your answer. Let's look at the following example. Suppose that f is defined recursively by f0 equals to 3, fn plus 1 equals to 2fn plus 3. Find f1, f2, f3, and f4. To solve this question, let us see f1. To get the f1 value, we must multiply 2 by the f0 before adding 3, giving us 9. To get the value of f2, we must multiply 2 by the f1 before adding 3, giving us 21. The same process is conducted for f3 and f4 as shown on the slide. Can you understand so far? Two steps need to be taken to prove recursive definition using mathematical induction. The two steps are the base step, which specifies the value of the function at 0, and the recursive step, which gives a rule for finding its value. Let's look at the example on the slide. We are supposed to prove that for any n that is greater than or equal to 0, f3n is even. In the first step, we must show that p0 is true. When n equals to 0, 3n equals to 0. Since f0 equals to 0, thus it is proven that p0 is true. During the second step, that is the inductive step, we have to show that when pk is true, pk plus 1 must be true. Assume that pk is true, thus f3k is even. This step is also known as the inductive hypothesis. Next, we must show that pk plus 1 is also true. Thus, we replace n with k plus 1 as shown on the slide. From the equation, we have to expand the bracket to get f3k plus 3. Based on the Fibonacci numbers, fn equals to fn minus 1 plus fn minus 2. If n equals to 3k plus 3, thus f3k plus 3 will give us f3k plus 2 plus f3k plus 1. Remember to minus 1 for the first statement and minus 2 for the second statement. We have to conduct the same process for f3k plus 2 using the Fibonacci numbers, which give us f3k plus 1 plus f3k. Now, replace the new value for f3k plus 2 and remain the same for f3k plus 1. From the equation, the two values of f3k plus 1 can be added to get 2f3k plus 1. Thus, the final answer is shown on the slide. Since we have 2 in the equation, it is proven that it is even. In conclusion, we can say that by the induction hypothesis, f3k is even. 2f3k plus 1 is even because it is 2 times an integer. Thus, its value must be even. Hence, f3k plus 3 is even. You may check the answer as shown on the slide. It is proven that when pk is even, pk plus 1 is also even. I hope you can follow my lecture, and if you have any doubt about any parts of the lecture, feel free to ask me using any medium you like. Please send me a message. I have watched your video using WhatsApp if you have finished watching my video as part of your attendance. Thank you for watching and have a nice weekend, students.